Hello, I'm Xiatian Zhang from Durham University. Today, I'm very glad to talk about my recent research on surgical workflow anticipation. So, what is the surgical workflow anticipation? It's a kind of technique to predict when the next step will happen in an operation. This technique can provide a more efficient collaboration for the surgery team because they can know the remaining time before the next step and have more time to prepare for that. Besides that, the surgical workflow anticipation is also a critical task for the automatic surgery because only robots know when the next step will be done. Then it is possible to achieve a fully automatic system. So how did the previous studies deal with this task? The baseline architecture for this task will normally consist of two parts. The first part is a backbone to extract the visual information for each frame of the surgical videos by convolution neural networks. The second part is a network for temporal feature modeling. And in 2021, Yuan's team introduced more backbones into the first part and got a state-of-the-art performance. On the left-hand side of this page, here are more details about Yuan's work. They not only used the visual information, but also used the recognition results for the current and previous instruments and phases, the bounding boxes of the surgical instruments, and the semantic segmentation maps for the surgical scenarios. This design can give their network multiple sources of information to have a more comprehensive understanding of surgical scenarios. But it will also increase the training costs. So in our work, we assume that only the geometry information of surgical instruments, which is the bounding box in this sample figure, can also give enough information for surgical workflow anticipation, because the geometry information of the surgical instruments can already have much motion information of the surgical instruments, which is critical in the surgical workflow understanding. And our design can also save more training costs than Yuan's work. So how do we use the geometry information in our work? We design a spatial-temporal graph representation for instrument motion information and their interaction. We let each instrument with each bounding box information as a node in a graph space, and link the different nodes to represent the interaction relationships between instruments in each frame. And we also link different nodes in different frames to represent the temporal relationships in the surgical videos. We assume the graph structure of surgical instruments can contain enough information for surgical understanding. Here are more details of our graph design for each frame. Each node of our graph will contain the coordinate and size of each instrument. And we also add an all zero value node to represent the surrounding environment in our graph. The links in our graph are designed under prior medical knowledge that the grasper and hook are the most commonly used instruments in the surgeon data. So we will mainly focus on the interaction between these two common instruments and other instruments. Then, we will talk more about our network architecture. After getting our graph representation, we will input our graph data into graph convolutions to model the relationship between nodes within each frame, and then use the temporal convolutions to model the temporal relationships between different frames. Finally, we will get our final anticipation results through two-layer fully connected layers. More details about our network architecture can be found in our paper. We will only show the details of our graph convolution today. Our graph representation for each frame could be transformed into an adjacent matrix. The core idea of our graph convolution is to combine this adjacent matrix with convolutions, so that we could add the graph constraints into our network. After network design, we will talk about matrix and loss in our system. Here is an example output figure of our system. The black line is the ground truth and the green line is our output. In the anticipation task, there is an example concept called horizon. It means the time range to anticipate. The horizon part is the decreasing line in the example figure. For example, if the horizon is 5 minutes, our system needs to capture the next step that happens in the next 5 minutes. And in this work, we will focus on the performance of our system when the next step will really happen in the horizon. That can be evaluated by inMAE and eMAE. We will also focus on the performance of our system when the system thinks the next step will happen in the horizon. That can be evaluated by the pMAE. And to ensure our system can meet the performance in different conditions, our training loss will be the combination of this matrix. Then, here are some details about our experiment. We will validate our system on the QUALITATIVE dataset. It is a very popular cholecystectomy video dataset in surgery data science. And we will try a YOLO wave file backbone to detect the bounding boxes of the surgical instruments. And the test performance in our work will be validated by online inference. That means anticipation on each frame can only rely on previous and current information. And here is our system performance compared with the state of the art. That can show our system can achieve comparable performance with the previous work. Because our system will use less training cost, our system can be considered with some advantages in data efficiency. After that, this is the application study of our system. It can show the combination of all components of our system can achieve the best performance. That can demonstrate the benefit of each component of our system. Then, here is the qualitative example of our system output. It can show our system can work well for most instruments but irrigators. That may be because the usage of irrigators can be related to the bleeding event, but our current system still cannot include enough details of environmental information. So, one of the main limitations of our current work is that our system may not have enough representation for surrounding surgical information, and sometimes our system performance may be also affected by the performance of bounding box estimation. So in our future work, we will try to improve our representation work for a more robust and comprehensive representation. In addition, we will also try to validate the performance of our system on different datasets and different matrix sites. In conclusion, we propose a graph representation learning-based way for surgical workflow anticipation to use the geometry information of surgical instruments. The graph representation is effective to deal with the surgical workflow anticipation. Future work includes a more dynamic representation of surrounding surgical information. Here is the reference list of this presentation. That's all about today's presentation. Thank you very much for your time and attention. Please feel free to email me if you have any queries or comments on our work.